So let's take this information and finally build up and add to our knowledge of the model of the atom. So what we know, what we knew going in, the nucleus has protons and neutrons in the center. The atom is mostly empty space. The electrons are somewhere. Um, Energy levels exist and electrons do something in them, right? So they exist in an energy level, and changing the energy of the atom can change the level the electron is in, but the electron can also move back down. Um, and then if we try to measure an electron, its properties change. If that last sentence seems weird, doesn't quite make sense, make sure you've watched the Dr. Quantum video. Okay, so I have actually some really good news. So from Heisenberg uncertainty, we know you can't know the wave information and the particle information about these objects both very well. The good news is the energy of an electron is more important than its position. So if we have a big uncertainty in position, that's okay. We're just going to accept it because the energy information is more important. So where this leads us is to talk about where the electrons exist. So how are we dealing with the uncertainty in position? What are we going to use to represent it? What does it mean? And so on. So an orbital is where an electron lives. We can calculate the energy of orbitals with the Schrodinger equation, which is this h psi equals e psi. And psi is the wave function. And by wave function, I really do mean an equation that looks like it would give you a wave. So cosine theta, sine of phi type of equation. The h with the little hat, this is a Hamiltonian operator. So the interesting thing about Hamiltonian operators is that if you take the wave function and you apply the Hamiltonian operator, the output that you get is the wave function and its energy. Now, that sounds way more simple than it is to actually do. It requires more calculus than I ever want to know, and is like a junior level class if you are a chemistry major and are continuing on. So we don't have to try to solve this equation, but this is the equation that we would use. And also Hamiltonian operators can be looked up in a table so that it can be used. And out of all of this, right, since we can't know the location very well, we take that wave function and we square it, and psi squared will help us represent the probability of finding an electron within some area of a sketched shape. We usually stick to about 90% probability, and that's good enough. And so that's what an orbital is. It's this sketched shape of a 90% probability that we will find an electron or one or two specific electrons in there. So what we're going into next is how do we identify different orbitals, and then we will sketch some of their shapes because these shapes are well known. Right, the electron's in there somewhere. We don't know exactly where it is, but we know the shape of the 90% probability. So we identify orbitals with quantum numbers. N, we call it the principal quantum number. This is that same n value that we had with the Bohr model of the atom. So n equals 1 is the lowest, and it's the lowest energy. Then we can go up from there in whole numbers. This principal quantum number tells us about the size and the energy. So going up in n means going up in size and up in energy. There's also a quantum number that we label as L. That's the angular momentum quantum number. And this gives us the general shape. So the angular momentum quantum number, it can be 0, 1, 2. It also goes up in whole numbers, but the limit is n minus 1. So that means if n is 1, n minus 1 is 0. So the limit at n equals 1 is this one value of L equals 0. So this, right, if this is telling us the shape, that means at the ground state level, there's only one shape of orbital that we're going to see. When n is 2, the limit is n equals 1, and we will have everything in between. So at n equals 2, we will have L equals 0, so we'll have some shape that is the same as the n equals 1 level, but it'll be bigger and at a higher energy. And we'll also have L equals 1. So now we'll have a different shape that is available at n equals 2 that was not available at n equals 1. N equals 3, right? We're just going to keep adding. So 3 minus 1 is 2. So the limit is L equals 2. But we will also still have L equals 0, L equals 1, and now L equals 2. So same shape, higher energy for 0, same shape, higher energy for 1, new shape for 2. And what you might know these as, if you've done any chemistry before, is that these shapes, we just give them letter designations. So instead of always calling it L equals 0 shape, it's the shape of an s orbital. So when L equals 0, we're talking about s orbitals. When L equals 1, it's a p orbital. L equals 2 is a d orbital. L equals 3 is an f orbital. That's, I mean, really the limit of what you're going to have to deal with is probably d orbitals, but f orbitals, right, we'll see some things in the periodic table that make f orbitals important, but that's about it. These are named for things that were seen on the atomic spectra that kind of came out of like the lines that were seen and whether they were sharp or diffuse, right? That's how we got S and D. And then it ends up relating to the orbitals in which, I honestly can't remember, the electrons originated, I believe, for the transition that was seen in the spectrum. Now, beyond this, right, we have these fancy letters S, P, D, F. If you go up to L equals 4, there's no fancy letter after that. We just continue the alphabet. So L equals 4 is G because it comes after F, and L equals 5 is H because it comes after G. You won't have to deal with G and H orbitals except for in theoretical circumstances. The third quantum number is the magnetic quantum number. This identifies specific orbitals and tells us how many are in a set. So this range is from minus L to plus L, and it goes up by 1 in between those two. So as an example, when L is 0, well, from negative 0 to positive 0, M sub L is only 0. So there's only one value, which means that within an energy level, so with a principal quantum number, there's only one s orbital. So if my principal quantum number is 4 and I'm specifically looking at the L equals 0 that is available to level 4, that is my 4s orbital, there's just one 4s orbital. If we go up to L equals 1, now my range is minus 1 to plus 1 with everything in between. So minus 1, 0, and plus 1 are my options. This means that when I have the availability of L equals 1, which is the p orbital, then what I really have is a set of 3 p orbitals. One could be identified by the negative 1, one could be identified by the 0, and the other could be identified by the plus 1. Then the d orbitals, so L equals 2, range of negative 2 to plus 2. If you fill this in from negative 2 to plus 2, there are 5 d orbitals. Now, you should be able to go to L equals 3 and write out the range of M sub L values that exist for L equals 3, and show that there are 7 f orbitals. Now, I'm not going to make you draw f orbitals, but where we will end up is drawing the shapes of the s orbitals, the set of 3 p orbitals, and the set of 5 d orbitals. The last quantum number is the spin quantum number. We label this as m sub s, and it kind of, right, we don't need it to draw the shapes because the L and the m sub L gives us all of the information that we need to draw the shapes, but we will need that m sub s to identify a specific electron in an orbital. So when we get to, I think it's in module 6, honestly, when we get to looking at specific electrons going into specific orbitals, we'll then be able to, with quantum numbers, give kind of the address of that electron.